Welcome to Science Reshaped, where data becomes discovery. If you're here for real, verifiable space science told clearly and calmly, tap subscribe and stay with me. Today we're unpacking a headline that genuinely moved the goalposts. 3I Atlas is not what we thought. James Webb's discovery. Let's set the stage. Astronomers monitor the sky constantly with automated surveys that flag faint, moving points of light. One of those survey systems picked up a new object in mid-2025. Follow-up measurements showed its path wasn't an ellipse bound to the sun, but a hyperbola, the unmistakable signature of an interstellar visitor. It was designated 3I Atlas, the third confirmed object ever observed coming from outside our solar system, after 1I, Oumuamua, 2017, and 2I, Borisov, 2019. From the moment its trajectory was solved, telescopes across the world and in space pivoted to watch. Interstellar bodies are time capsules from other planetary systems. They carry chemistry forged around another star. The expectation, based on Borisov and on many solar system comets, was straightforward. Water ice would dominate the outgassing, as warming sunlight liberated subsurface H2O with familiar traces of CO, CO2 and organics. That's not what happened. When the James Webb Space Telescope, JWST, obtained spectra of 3I Atlas, the surprise was immediate and unambiguous. Carbon dioxide, not water, dominated the coma by a large margin. Water was present, but the CO2 to H2O ratio was unusually high, far outside the norm for typical comets. In practical terms, the jets powering its activity were mostly CO2-driven. That single fact forced a rethink. We weren't looking at pristine ice, lightly warmed into venting. We were looking at ice that had been chemically processed for a very long time. Here's why that matters. In deep space, beyond the sun's protective magnetic bubble, solid surfaces are bombarded for eons by galactic cosmic rays, high-energy particles that smash molecular bonds and reassemble atoms into new compounds. Lab experiments and models agree. Over millions to billions of years, those particle hits gradually convert carbon monoxide into carbon dioxide, darken and densify organics, and build a radiation-processed mantle tens of meters thick. JWST's reading of a CO2-rich coma is exactly what you'd expect if 3I Atlas had worn such a mantle and was now venting from it. In other words, we're not just seeing where the object formed, we're seeing what interstellar travel does to country materials. That reframes the scientific value of these visitors. Before 3I Atlas, many hoped an interstellar comet would be a clean snapshot of a foreign protoplanetary disk. Chemistry frozen at birth. 3I Atlas tells a subtler, arguably deeper story. Time and exposure matter. Interstellar objects may arrive evolved, their outer layers rewritten by the galaxy itself. If you want the untouched material, it may be buried beneath a processed crust we can't directly sample with remote telescopes. Other telescopes added crucial pieces. Photometry showed an unusual brightening behavior as the object approached the sun, faster and more erratic than many solar system comets at comparable distances, followed by plateaus and dips. A leading explanation is mechanical. As sunlight penetrated the hardened exterior, pressurized CO2 pockets ruptured, producing brief, powerful jets. Each event threw off darker, larger dust grains enriched in complex carbon compounds, consistent with a surface that has been baked by radiation into sturdier, lower albedo particles. Polarimetric observations, measurements of how light is polarized by reflection and scattering in the coma, reported a particularly strong negative polarization at small phase angles, a combination not commonly seen. Negative polarization is normal for dusty comae at certain geometries, but the magnitude and angle at which it peaked hinted at unusual grain size, structure, or composition. That, again, lines up with a mantle of radiation-hardened material, whose microtexture isn't the same as freshly exposed, fluffy, ice dust aggregates. Meanwhile, ultraviolet and X-ray assets monitored for OH hydroxyl emission, the telltale fragment produced when solar UV splits water vapor. Detections of OH and H2O confirmed that water was indeed present, just not in charge, the coma. Chemistry consistently put CO2 in the driver's seat, with water playing a secondary role. Traces of CO and simple organics rounded out a picture of an object whose outer skin bears the scars of deep time. Trajectory-wise, 3I Atlas followed a retrograde, slightly inclined hyperbola into the inner solar system, reached perihelion in late October 2025, and arced back out. There was no impact hazard. Its closest approaches were measured in astronomical units, not planetary radii. But scientifically, that close solar pass was a gift. It turned the object into a controllable experiment. As solar flux rose, the coma, composition and dust response changed measurably, letting researchers test models of thermal diffusion, vent opening, and jet turnoff through a processed crust. So why does JWST's result earn the headline, "Not what we thought"? Because it compels a paradigm shift. For decades, the working assumption was that interstellar comets might look like Borisov, but from elsewhere. Water-rich, broadly familiar, pristine snapshots of alien chemistry. 3I Atlas demonstrates that interstellar objects can arrive chemically matured, their spectra shaped less by their natal disk and more by cosmic ray processing during interstellar flight. That doesn't make them less valuable. It changes the questions we ask. Instead of, what was the original mix? The sharper questions are, how deep is the processed layer? How efficiently does it vent? Which molecules survive? And how does the galaxy's radiation environment imprint itself on small bodies? There are practical consequences. Mission planners thinking about a rapid response flyby or rendezvous, concepts akin to ESA's Comet Interceptor, now know they must be ready for CO2-dominated activity, dark, consolidated dust, and surfaces that might withstand heating until stress fractures open. Instruments must be tuned to probe subsurface thermophysics and radiation products, not just fresh frost. Models used to invert spectra into composition will need to account for mantle depth, porosity evolution, and cosmic ray dose over giga-year timescales. There are also broader cosmic implications. If 3I Atlas is representative of long-haul interstellar bodies, then interstellar space itself becomes a chemistry lab, not empty, but transformative. The galaxy doesn't just shuttle building blocks, it refines them. That viewpoint helps reconcile why different interstellar visitors can look so different. 2I Borisov may have been observed with less processed ice exposed, whereas 3I Atlas showed us the processed face of the same overarching story. Formation, ejection, drift, irradiation, reactivation, finally, context. We now have 3 data points across 8 years. A puzzling, likely dry 1I Oumuamua, a water-forward 2I Borisov that looked comet familiar, and a CO2-forward 3I Atlas whose surface chemistry screams deep time. With that trio, the field is moving past anecdotes and into comparative interstellar planetology. Each new visitor won't just answer what is it made of, but also what has the galaxy made of it. In the next part, we'll break down how astronomers read chemistry in motion from light, what Webb's spectra actually measure, why CO2 lines stood out so clearly, how water was confirmed even when it wasn't leading, and what the dust told us about grain size and texture. We'll also look at the unusual brightening curve near perihelion and what it reveals about the physics of jetting through a radiation-hardened crust. Stay with me. The details here are where the discovery truly lives. The next step after confirming 3I Atlas's interstellar origin was to decode what its light was actually telling us. The Webb telescope's spectrometers recorded its glow in infrared bands, where ices and gases leave their signatures, tiny dips and spikes that correspond to specific molecules. From those lines, scientists extract chemistry, temperature, even dust size. And in 3I Atlas's spectrum, the pattern was unmistakable. Carbon dioxide features towering above the faint traces of water. For context, most solar system comets show the opposite. When they warm, frozen H2O sublimates first, driving fountains of vapor that drag dust outward. CO2 usually appears as a secondary component. Here, it was reversed. water lines almost drowned beneath carbon dioxide bands. That meant the comet's outer layers were richer in CO2, or that water lay buried under material so compact that sunlight could not reach it. Either way, the ratio was far outside the norm. To confirm, ground observatories and NASA's Swift satellite monitored in ultraviolet wavelengths, watching for hydroxyl, an indirect marker of water vapor. They did detect it, proving that water was present, but comparatively weak. So the first firm conclusion stood: 3I Atlas vents primarily CO2. That alone would make it chemically distinct from every known solar system comet. From there, astronomers turned to physics. Why would a nucleus favor carbon dioxide emission? The best explanation links to the cosmic ray processing theory. Over millions of years in interstellar space, high-energy particles bombard frozen surfaces, breaking apart carbon monoxide molecules and recombining them into CO2. Each impact deposits energy, driving slow chemistry that turns bright, porous ice into a darker, tougher crust. When such a body finally enters a star's warmth again, that crust cracks, releasing CO2 long before underlying water can vaporize. The Webb data matched that model precisely. Understanding those details matters, because each one refines our models of interstellar object survival. A body ejected from its home system must endure extremes: cosmic ray bombardment, ultraviolet exposure, micrometeoroid impacts, and absolute cold for perhaps billions of years before entering another star's domain. What we saw with 3I Atlas is evidence that material can indeed survive that journey, but it doesn't stay untouched. It evolves into a new, radiation-mature state. Researchers also examined the comet's backward trajectory to estimate origin. Its velocity, about 26 kilometers per second relative to the Sun, implies a long, slow drift through the local interstellar cloud. Tracing its path beyond that point becomes impossible because nearby stars have shifted positions over millions of years. Still, simulations show that objects ejected from planetary systems are common, suggesting our galaxy may teem with similar wanderers, invisible unless they pass close enough for sunlight to wake them. All this leads to a broader understanding. The space between stars is not a void, but a chemical refinery. 3I Atlas demonstrates that interstellar radiation fields actively modify small bodies, producing complex organic residues and stabilizing carbon dioxide over vast timescales. Such processes could seed planetary systems with pre-processed organic matter long before planets themselves form. As it receded after perihelion, the comet's activity declined predictably. Water signatures strengthened briefly, confirming that deeper layers were finally warming, but overall brightness fell as the object moved outward and the jets subsided. By late 2025, it had faded beyond the reach of most telescopes, leaving behind terabytes of data now archived in international databases for years of analysis. What those data reveal is a quiet revolution in comet science. Before 3I Atlas, interstellar bodies were seen as snapshots of their birthplaces. After it, they are recognized as witnesses to the galaxy's radiation history. Each visitor records not just where it came from, but everything it has endured on the way. That makes them invaluable laboratories for studying long-term chemical evolution, processes we can't reproduce on Earth. In short, 3I Atlas forced astronomers to replace the image of a pristine alien snowball with that of a seasoned traveler, scarred, altered, but still active. Its chemistry tells us that the galaxy's radiation doesn't destroy complexity, it transforms it. The same carbon-rich crust that hides its origin may also preserve molecules that link star systems in a continuous cycle of matter. The scientific lesson is simple, yet profound. Interstellar comets are not relics frozen in time. They are records still being written. Every burst of gas, every spectral line, is a line in that ongoing log of the galaxy's chemical story. In the next part, scientists move from chemical composition to physical structure. How dense the nucleus might be, how deep the processed layer extends, and what that tells us about the mechanics of surviving a billion-year voyage through interstellar space. With the chemistry of 3I Atlas now firmly established, astronomers turned their attention to something even more fundamental: its structure. What kind of body can survive billions of years in deep space? enduring radiation and micrometeorite impacts, and still release gas when it enters a new star system? The answer required combining every clue: light curves, coma morphology, gas production rates, and rotation behavior. The first question was size. Observations from multiple telescopes indicated that 3I Atlas's brightness corresponded to a nucleus roughly 400 to 800 meters in diameter. That's small, barely half the length of a skyscraper, yet massive enough to retain ices deep beneath its surface. If true, its small size explains why it brightens so sharply when sunlight finally reached those pockets of gas. A smaller body warms faster, triggering abrupt outbursts rather than slow, steady sublimation. Its density is less certain, but models suggest something between 0.3 and 0.6 grams per cubic centimeter, similar to loosely bound rubble pile comets. That means it isn't solid rock. It's a fragile aggregate of dust and ice grains held together by weak gravity. But after billions of years, such a structure should have disintegrated. So how has 3I Atlas survived intact across interstellar space? The leading idea involves its radiation-hardened shell. Over immense timescales, cosmic rays break molecular bonds in the outer layers, converting volatile compounds into long carbon chains, a process called graphitization. This dark carbon-rich layer acts as both shield and glue, toughening the surface and reducing vapor loss. Beneath it lies an intermediate region, the transition zone, where cosmic rays partially penetrate, creating complex molecules like methanol and formaldehyde. Deeper still, beyond about 15 to 20 meters, the core remains pristine, untouched ice from the object's birth system. When 3I Atlas entered the Sun's domain, heating began to erode that protective shell. Gas built up behind it, fracturing the surface and exposing fresh layers. Each crack became a vent, releasing CO2 jets and throwing dust outward. This activity carved patterns that telescopes detected as changing brightness. In effect, astronomers were watching the comet's geology unfold in real time. Studying these jets provides another kind of information: rotation. Each jet acts like a small thruster. By measuring how brightness oscillated over time, scientists estimated a rotation period of about 10 to 12 hours. However, those oscillations didn't follow a single repeating pattern. They varied, implying the body is tumbling rather than spinning smoothly. This chaotic motion probably began long ago when an earlier outburst imparted uneven torque. Tumbling further supports the idea that the nucleus isn't rigid but porous and lightweight. That fragile interior also helps explain 3I Atlas's unique coma, the cloud of gas and dust surrounding it. Instead of forming an elegant, symmetric tail like Borisov's, the coma of 3I Atlas looked irregular, even lopsided. High-resolution imaging revealed denser plumes extending in different directions, corresponding to specific vent regions. These asymmetries show that gas release depends not just on sunlight, but on how cracks expose buried ices along a tumbling surface. Researchers simulated this behavior using thermal models. They found that the CO2 sublimation front, the depth where CO2 ice begins to vaporize, moves inward unevenly depending on local crust thickness. Where the crust is thin, gas escapes freely. Where it's thick, pressure builds until it fractures. This constant cycle of sealing and breaking gives rise to the erratic activity patterns recorded in late 2025. Another surprise came from the dust itself. Polarimetric and photometric data showed that the emitted particles were larger and darker than those of typical comets. The average size exceeded a few micrometers, and their albedo, the fraction of light they reflect, was very low. That combination suggests carbonaceous grains, not bright silicates. Laboratory analogues confirm that prolonged radiation turns icy grains dark by forming tholin-like compounds, complex organic polymers that absorb visible light. In other words, interstellar travel has painted 3I Atlas in the black hue of cosmic aging. The comet's mass loss rate, the amount of material ejected per second, was another important measurement. Despite its strong CO2 outgassing, the total production was modest, only a few kilograms per second. For comparison, active solar system comets can lose hundreds of kilograms per second near perihelion. The difference arises because 3I Atlas's small size limits its surface area, and much of that surface is still sealed under hardened crust. Yet even those small releases were enough to generate the visible coma we observed from millions of kilometers away. Scientists also examined how deeply sunlight could penetrate into the crust. Using thermal conductivity models, they found that the top few centimeters, reached temperatures high enough to sublimate CO2, but water remained frozen until the comet was much closer to the Sun. That matches observations. The first clear signs of water vapor appeared only near perihelion, confirming that deeper, pristine layers were just beginning to thaw. By the time the comet moved outward again, activity dropped rapidly, and the outer crust began refreezing, sealing the interior once more. These measurements, size, rotation, density, dust, and gas, converge on a picture that's as poetic as it is precise. 3I Atlas is a survivor of two histories: the violent birth of a foreign solar system and the slow sculpting of interstellar time. Its body records both. The pristine core tells of formation, while the irradiated shell narrates endurance. And this realization has practical consequences. Space agencies planning future missions now see interstellar comets not as passive snowballs, but as evolving archives. Any probe hoping to sample them must drill past radiation-hardened crusts or capture freshly ejected material before it mixes with solar radiation. Even remote sensing strategies are adapting. New instruments are being designed to detect signs of processed ices and carbonized dust. But perhaps the most profound outcome lies in what 3I Atlas tells us about the connectivity of planetary systems. Its survival means that solids formed around one star can traverse the galaxy and enter another's gravitational reach intact. Over billions of years, such travelers could exchange materials between systems, spreading organic compounds far beyond their birthplace. This natural circulation suggests that the galaxy itself behaves like one vast chemical ecosystem. For decades, the notion that material from one planetary system might seed another was theoretical. Now, with data from objects like 3I Atlas, it's observational. Each interstellar comet acts as both messenger and cargo, carrying altered molecules forged in alien light, reshaped by cosmic radiation, and finally released in the warmth of our Sun. By the end of 2025, 3I Atlas had faded from view. Its retreat marked the end of its brief visibility, but the beginning of a long legacy. The data collected, spectra, brightness curves, polarimetric readings, will fuel years of study. Already, new models of cosmic ray chemistry are being recalibrated using its properties. Some of the same signatures seen in 3I Atlas are now being sought in the diffuse interstellar medium, linking a single comet to the broader galactic environment. In a sense, 3I Atlas has become the galaxy's emissary, showing that even in the coldest darkness, matter never stops changing. It records not a single moment in time, but an entire timeline of survival, from formation, through exile, to rediscovery. In the next part, we'll explore how scientists use these findings to reconstruct the object's possible birthplace, tracing back its velocity and trajectory to the regions of the Milky Way it may have originated from, and what that tells us about how planetary systems across the galaxy form and share their building blocks. Once astronomers had mapped the chemistry and structure of 3I Atlas, the obvious next question was, where did it come from? Tracing the birthplace of any interstellar body is one of the hardest problems in celestial mechanics. Yet every measurement, speed, direction, light curve offers a piece of the puzzle, the object's hyperbolic. Orbit told us that it wasn't gravitationally bound to the Sun. Its incoming velocity, about 26 kilometers per second relative to our star, showed that it had been traveling freely through the galaxy for at least millions of years. By projecting its trajectory backward through space, researchers could see that it entered the solar system from a direction roughly aligned with the constellation Hercules, crossing the plane of the Milky Way at a steep, retrograde angle. That geometry alone made it nearly impossible that the comet had been perturbed out of our own Oort cloud. It had to have originated around another star. To reconstruct a possible origin, scientists used galactic dynamic simulations that include stellar motions over tens of millions of years. Because stars drift relative to one another, any ejected body's path becomes blurred after only a few million years. Small uncertainties in velocity translate to huge positional shifts. Nevertheless, by running backward integrations that considered the motions of nearby stellar groups, astronomers found that 3I Atlas might once have passed within a few light years of systems such as HD 186302, a Sun-like star in Hercules, or the Lacaille 9352 moving group. These aren't proven sources, but they lie along plausible corridors in galactic space where the comet's path could have originated. Whatever the exact birthplace, the mechanics are clear. In a young planetary system, large planets migrate through disks of icy debris. Gravitational interactions with those planets fling countless small bodies outward. Most settle into distant reservoirs, what our solar system calls the Oort cloud. But some receive enough energy to escape entirely. Each ejection adds a new traveler to the galaxy's invisible population of free-floating comets. Statistically, billions of such bodies must wander between stars at any given time, though only a handful will ever pass close enough to be seen. For 3I Atlas, that ejection likely happened billions of years ago. The object would have coasted through interstellar space, far from any significant source of heat, its interior frozen near 260 degrees Celsius. During that time, it experienced the slow, relentless rain of cosmic rays that transformed its surface. Occasional impacts by micrometeoroids may have chipped away loose dust, leaving behind a compacted crust, the same hardened shell now venting CO2 near the sun. One subtle clue to its age comes from isotopic ratios measured in its gas. Although the data are preliminary, the relative abundance of carbon-12 to carbon-13 and oxygen-16 to oxygen-18 appears close to galactic average values, not skewed like many comets from our own system. That neutrality supports the idea that it formed in a different stellar environment, perhaps around a star slightly richer in heavy elements than the Sun. It also implies that the material making up 3I Atlas is truly representative of the broader Milky Way rather than a local sample. If the comet did originate in a region similar to our outer solar system, its composition would have been dominated by carbon monoxide, methane, ammonia, and water ice. Over time, radiation would have processed these into CO2, methanol, and long-chain organics, exactly as Webb observed. That sequence, formation, ejection, cosmic ray alteration, matches both laboratory experiments and theoretical models of interstellar chemistry. Understanding this journey isn't just about tracing one comet's past. It helps us map the exchange network of the galaxy. Every planetary system likely sends material outward and occasionally receives debris from others. Such traffic means that interstellar space is continuously seeded with organic-rich particles capable of contributing to planet formation elsewhere. 3I Atlas is tangible evidence of that exchange, a piece of another world visiting ours. The trajectory analysis also revealed something intriguing about the population statistics of interstellar objects. If one telescope survey could detect a single faint comet like 3I Atlas in just a few years of operation, then the density of these wanderers must be much higher than previously estimated. Perhaps tens of thousands passing through the solar system at any moment, most too small or dark to notice. Future wide-field observatories such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to discover many more. Each detection refines our understanding of how planetary systems evolve and distribute matter across the galaxy. As data accumulated, another aspect of 3I Atlas's motion drew attention. Its rotation-induced wobble slightly altered the direction of its jets, changing the trajectory by a few thousand kilometers per day. By modeling these non-gravitational forces, scientists could estimate the thrust from its outgassing and cross-check the mass of the nucleus. The results agreed beautifully with previous size and density estimates, confirming that our mathematical models can describe even alien comets with surprising precision. The effort to trace its origin also revealed an elegant symmetry. When plotted on galactic coordinates, the outbound path of 3I Atlas roughly mirrors its inbound direction across the plane of the Milky Way. That means its next journey will carry it back into the interstellar medium, resuming a voyage through the same radiation fields that shaped it in the first place. For our instruments, its light will fade. For the galaxy, it will simply continue its endless orbit around the center, another silent messenger between stars. By late 2025, as the comet moved beyond the orbit of Mars, its activity decreased sharply. CO2 jets subsided, the coma collapsed, and it returned to a dormant state. Even in that quiet phase, astronomers continued to observe it, to measure how quickly brightness dropped, data that reveal how rapidly gases freeze back onto the surface. The decline followed an exponential curve typical of outgassing cessation, showing that the comet was sealing itself again for another long sleep. In the years to come, 3I Atlas will drift beyond the reach of our telescopes, carrying with it every trace of its passage through the inner solar system. Yet the lessons remain. We now know that interstellar comets are not fragile snowballs doomed to sublimate instantly. They are resilient archives, capable of surviving multiple stellar encounters. They show us that planetary systems across the galaxy are interconnected through a continuous flow of matter. The true importance of 3I Atlas lies not only in what it revealed about its own chemistry or structure, but in how it expanded the framework of planetary science. It demonstrated that the galaxy itself is a single, evolving ecosystem, a place where materials formed around distant suns can travel unimaginable distances and still whisper their stories when we learn how to listen. In the next part, we'll explore how scientists are applying what they learned from 3I Atlas to predict the future of interstellar object research, how new telescopes, rapid response missions, and improved detection algorithms will prepare us for the next visitor from beyond the stars. After 3I Atlas faded from telescopic view, scientists didn't stop studying it. In many ways, the real work was just beginning. The data collected across infrared, optical, and ultraviolet wavelengths became the foundation for something far larger, a blueprint for the future of interstellar object research. Every detail, the CO2-rich composition, the erratic brightening, the radiation-hardened crust, demanded a new kind of preparedness. Until recently, when astronomers thought about comets, they imagined centuries-old visitors from our own Oort cloud, easily predictable and chemically familiar. But 3I Atlas forced a paradigm shift. It showed that the next interstellar traveler could look and behave completely differently. And if we want to study it properly, we'll need to react faster and observe smarter. The most immediate challenge is detection. Atlas itself was discovered by a modest survey telescope only months before perihelion. That's barely enough time to organize a global observing campaign, much less prepare a space mission. But new instruments are about to change that. The Vera C. Rubin Observatory, expected to begin operation soon, will scan the entire sky every few nights with unmatched sensitivity. Its legacy, Survey of Space and Time, LSST, will capture faint, fast-moving objects far earlier than current systems. For interstellar research, that's revolutionary. If 3I Atlas had been detected 6 months sooner, Webb could have scheduled longer observations and measured isotopic ratios with higher precision. Beyond detection, the next step is rapid response missions. Space agencies are now designing probes that can launch on short notice to intercept a newly discovered interstellar object. The European Space Agency's Comet Interceptor, already under construction, is the prototype. It's a spacecraft that will wait at the L2 Lagrange point, ready to sprint toward any suitable target once one is found. Although built for a long-period comet, its instruments, high-resolution cameras, spectrometers, and dust analyzers, are perfectly suited to an interstellar visitor. The experience with 3I Atlas has informed how those instruments are calibrated. They must detect CO2-dominated outgassing, dark organic dust, and perhaps fragmented, low-density surfaces. Scientists are also rethinking how to read interstellar data. Before 3I Atlas, analysis pipelines assumed water would dominate a comet's spectrum. Now they must account for the possibility that cosmic ray chemistry can reshape an object's surface. Teams have updated modeling software to include radiation-driven transformation of ices, a process that may occur in every galactic environment. That's how deeply this single comet has influenced planetary science. It didn't just change our understanding of one object, it rewrote the assumptions behind an entire field. Then there's the search for origin patterns. With only 3 known interstellar visitors, Oumuamua, Borisov, and Atlas, statistics are thin, but early patterns are emerging. Each has shown distinct composition. Oumuamua appeared rocky, perhaps devolatilized. Borisov was water-rich and resembled solar system comets. Atlas was CO2 dominant and radiation altered. Together, they span the evolutionary sequence of small bodies across interstellar time. The next discoveries will help fill in the continuum, telling us how objects evolve from icy newborns to darkened relics drifting between stars. The James Webb Space Telescope will continue to play a crucial role. Its mid-infrared instruments can detect faint heat signatures that reveal molecular bonds impossible to study from the ground. If another interstellar comet appears within a few astronomical units, Webb can immediately analyze its surface chemistry with exquisite precision, something it barely had time to do for Atlas. Meanwhile, Ground-based observatories such as ALMA and the Very Large Telescope are refining methods to measure isotopic ratios and dust polarization, turning faint specks into fully characterized worlds. But the legacy of 3I Atlas extends beyond astronomy. Astrobiologists are paying close attention to its organic chemistry, the radiation-driven transformation that created complex carbon molecules on its surface may mirror what happens inside molecular clouds, the birthplaces of planets and, potentially, of prebiotic compounds. If CO2-dominated, radiation-altered comets are common, they might be vectors for organic enrichment, carrying preformed molecules from one star system to another. That idea, that life's raw ingredients can travel across interstellar space, is no longer science fiction. It's an active area of research inspired directly by 3I Atlas. There's also an important philosophical shift happening within the scientific community. Before 3I Atlas, many viewed interstellar visitors as isolated curiosities. Now they're seen as connectors, tangible proof that planetary systems are not closed loops, but participants in a galactic exchange. This means every observation of such an object adds to our understanding of the Milky Way as an ecosystem. Instead of studying just our sun and its planets, we're beginning to study how all stars share material across billions of years. Another exciting frontier involves machine learning. Data from 3I Atlas's detection are being used to train algorithms that can spot the subtle motion of faint objects against the crowded background of stars. Unlike traditional surveys that rely on human confirmation, these AI-driven tools can process petabytes of sky images in real time, identifying potential interstellar candidates days or even weeks earlier than before. Every extra day matters. It gives scientists time to schedule follow-ups, align telescopes, and maybe, just maybe, prepare a spacecraft for rendezvous. Even as we look forward, researchers continue to refine the details of Atlas itself. Deep analysis of its light curves has revealed subtle periodicities that could indicate structural asymmetries, perhaps internal voids or a partially fractured core. Laboratories on Earth are now recreating those conditions, exposing mixed ices to cosmic ray analog radiation, then warming them to see how they vent gases and crack apart. Those experiments will tell us whether Atlas's sudden flares were caused by volatile pockets or mechanical collapse. Step by step, a new science is emerging: interstellar small-body geology. We're beginning to treat these visitors not as fleeting dots, but as geophysical worlds shaped by both their birth and their voyage. Every measurement becomes a probe into how matter behaves when exposed to cosmic environments for unimaginable spans of time. Looking back, the story of 3I Atlas is a story of readiness. The discovery came just in time for JWST to observe it, yet too late for a dedicated mission to be launched. Next time we'll be ready. The infrastructure now being built, global coordination, rapid response launches, AI-based discovery pipelines, exists because of what we learned from this single carbon dioxide-rich wanderer. What once felt like a one-off cosmic event is now recognized as the start of a new era. The galaxy is full of travelers like Atlas. Some may be pristine, some scarred by radiation, some carrying the chemical whispers of life itself. Our challenge is no longer to ask whether we'll see another, but how soon, and how prepared we'll be when we do. In the next part, we'll follow that idea even further, exploring what these findings mean for our own solar system's past, and how studying 3I Atlas might help us understand the origins of comets, planets, and even life right here at home. By the time 3I Atlas disappeared into the dark, the astronomical community had already begun using its lessons to look inward, toward our own origins. Because if interstellar comets can travel from one planetary system to another, enduring for billions of years and carrying processed organic matter, then perhaps the story of our solar system's formation is not as isolated as once believed. Planetary scientists began asking a radical but natural question. Could the early solar system itself have been seeded by interstellar debris like 3I Atlas? To explore this, researchers revisited models of the Sun's birth environment. Our Sun likely formed in a dense stellar nursery, a cluster containing thousands of young stars packed within a few light years. In such clusters, gravity constantly flings small bodies from one newborn system to another. The result is a rich exchange of material: icy comets, carbon dust, even complex molecules hopping between young stars before planets have fully formed. This idea isn't new, but for decades it lacked evidence. Now, with 3I Atlas, 2I Borisov, and 1I Oumuamua as tangible examples, the theory has become much harder to ignore. Each object demonstrates that solid material can survive interstellar travel, not just gas or dust. That survival changes everything, because it means chemical information, and possibly the precursors of life, can migrate across the galaxy. The chemistry of 3I Atlas fits that scenario perfectly. Its carbon dioxide and organic-rich composition suggests that such travelers don't merely carry frozen water and rock. They also transport chemically evolved carbon compounds, the same kinds detected in meteorites and interplanetary dust within our solar system. When heated, these materials can produce amino acid precursors, formaldehyde, and sugars, molecules central to prebiotic chemistry. In other words, the building blocks of life may have been circulating between stars long before Earth even existed. That possibility has inspired a new generation of research into galactic panspermia, not in the speculative sense of life itself spreading between worlds, but as an exchange of raw materials. 3I Atlas provides the first direct evidence that interstellar space does not sterilize matter, it transforms it. Radiation turns simple ices into more complex organics that remain stable for billions of years. When these materials eventually fall into a young solar system, they can mix with local matter, influencing the chemistry of future planets. To test this, laboratories have begun simulating the surface conditions of 3I Atlas. Using cryogenic chambers, scientists expose mixtures of carbon monoxide, methane, and water ice to high-energy protons, analogues of galactic cosmic rays. After weeks of exposure, the ices darken and form carbon dioxide, methanol, and tar-like organics nearly identical to those inferred from the comet's spectrum. When warmed, these samples release CO2 in sudden bursts, mimicking the venting patterns that telescopes observed as Atlas approached the Sun. The match is remarkable. It proves that interstellar radiation can not only process icy material, but preserve it in a chemically rich, metastable state for immense timescales. From a cosmic perspective, that means 3I Atlas isn't unique. It's a representative of countless interstellar carriers that have likely been weaving through the galaxy for eons. And if some of those entered our proto-solar nebula 4.6 billion years ago, they could have delivered complex organic compounds to the disk that formed Earth. This insight is reshaping how scientists think about the origins of organic matter in our own comets and meteorites. What we once considered purely solar system chemistry may, in fact, include galactic contributions. The evidence supporting this idea is mounting. Samples returned by NASA's Stardust mission from Comet Wild 2 and from the Ryugu and Bennu asteroid missions contain organics that show isotopic anomalies inconsistent with formation in the solar system alone. Some of those isotopic ratios match what we would expect from interstellar grains exposed to cosmic rays, the same kind of processing seen in 3I Atlas. It's as if pieces of other solar systems are already embedded within our own. That concept also reframes how we interpret meteorites that fall to Earth. Many carbonaceous chondrites contain pre-solar grains, microscopic crystals older than the Sun. Now, with 3I Atlas as a working analog, we can imagine entire comets carrying such grains through space, each one a miniature archive of galactic history. The solar system, it turns out, is not a closed box. It's a collector, a receiver of messages in the form of dust, ice, and molecular memory. At the same time, the study of 3I Atlas has deepened our understanding of what interstellar radiation does to matter. The transformation of CO to CO2 and the creation of refractory organics demonstrate that energy and chemistry don't stop between stars. They continue at a slower, subtler pace. That process may even help explain why carbon-based molecules are so abundant throughout the cosmos. They're constantly being cooked, shattered, and reassembled by the very radiation that fills interstellar space. In this sense, 3I Atlas isn't just a traveler. It's part of the galaxy's carbon cycle, endlessly transforming matter from simple to complex and back again. Beyond chemistry, there's also a dynamic lesson. 3I Atlas's survival through billions of years tells us that small bodies can endure far longer than we thought. Its dense, radiation-hardened crust may be precisely what allowed it to remain intact, despite the harsh environment of interstellar space. That crust, in turn, acts as a shield, preserving volatile ices and organics beneath. The same principle could apply to ancient comets still residing in our own Oort cloud. Perhaps many of them also bear the chemical fingerprints of radiation exposure that predates the solar system. For astrobiologists, these insights are transformative. The boundary between local and interstellar chemistry is dissolving. The molecular building blocks of life may not originate in any one place. They may be a shared inheritance of the galaxy itself. If so, the emergence of life on Earth was not an isolated miracle, but a natural outcome of processes that happen everywhere, all the time, wherever radiation meets ice and time. This understanding has philosophical weight too. It suggests that the story of life doesn't begin with Earth. It begins with the chemistry of the galaxy. Every comet, every grain, every interstellar wanderer is part of that larger continuum. 3I Atlas simply revealed the connection in a way we could finally measure. As scientists refine their models, one message grows clear. Interstellar comets like Atlas are not just curiosities. They are keys to understanding the shared origin of all planetary systems. They teach us that creation, transformation, and preservation are not sequential events but simultaneous forces acting across the universe. And perhaps the most humbling realization is this. When we look at 3I Atlas, we're not observing a foreign visitor. We're seeing a reflection of ourselves, of the same cosmic matter, the same chemistry, the same galactic journey that led to our own existence. In the next part, we'll explore how these revelations are reshaping future mission designs, from robotic probes capable of intercepting interstellar objects to sample return concepts that could, one day, bring back a true fragment of another star system for study on Earth. The revelations sparked by 3I Atlas changed not only how scientists think about interstellar matter, they also changed how we plan to explore it. For decades, every space mission was designed for predictable targets: planets, moons, asteroids, and periodic comets whose orbits could be charted decades in advance. But interstellar visitors don't give us that luxury. They appear without warning, stay for a few months, and vanish forever. If we ever want to study one up close, we need to be ready long before it arrives. That challenge has now become one of the most exciting frontiers in planetary exploration, the era of rapid response missions. The blueprint was inspired directly by lessons from 3I Atlas. When Atlas was detected in mid-2025, it took just days for astronomers to confirm its interstellar nature. Observatories worldwide coordinated follow-ups, and space agencies scrambled to schedule telescope time. It was an extraordinary effort. But by the time the James Webb Space Telescope completed its observations, the comet was already near perihelion and heading outward. There was no chance to send a probe. That frustration led mission planners to ask a simple question. What if we had a spacecraft always waiting, ready to launch the moment such an object appeared? The European Space Agency's Comet Interceptor, due to launch in the late 2020s, is the first step toward that vision. It will park at the Sun-Earth L2 Lagrange point, a gravitationally stable position roughly 1.5 million kilometers away, and remain dormant until a new comet or interstellar object is discovered. Then, using onboard propulsion, it can sprint to intercept the target. Its instruments are being tuned based on the chemistry and physics revealed by 3I Atlas, spectrometers sensitive to carbon dioxide and organics, dust analyzers capable of detecting dark, radiation-processed grains, and cameras designed to capture rapid, unpredictable outbursts. NASA, meanwhile, has studied concepts for even faster response missions, including interstellar interceptors that could remain in solar orbit for years, powered by solar sails or advanced ion engines. These vehicles would not wait near Earth. They'd patrol the inner solar system like sentinels, ready to change course toward any new incoming object. All of this traces back to a realization made painfully clear by 3I Atlas. By the time we spot an interstellar visitor, it's already halfway through its visit. To support those missions, detection technology is also evolving. Next-generation surveys like the Vera C. Rubin Observatory's LSST will image the sky so deeply and frequently that interstellar objects may be identified years earlier than before. The key lies in recognizing hyperbolic motion, the subtle curve that signals an object isn't bound to the sun. artificial intelligence will assist by filtering millions of moving points of light, learning to distinguish true interstellar trajectories from near-Earth imposters. These algorithms are being trained on synthetic data generated from the 3I Atlas and 2I Borisov trajectories. What once took weeks of manual confirmation will soon take hours. In parallel, astrophysicists are refining spectroscopic fingerprinting. 3I Atlas taught us that chemical anomalies, like extreme CO2 emission or unusually dark dust, can hint at interstellar origin even before orbital data are complete. Future telescopes will use this chemical recognition to trigger automatic alerts, giving scientists precious time to mobilize follow-up resources. But the biggest leap may come from something even bolder: sample return missions. Imagine capturing actual grains or gas from an interstellar object, material formed around another star, preserved for billions of years and delivered to our laboratories. The idea once seemed impossible, but technology is catching up. Design studies now explore fast intercept trajectories using high-thrust chemical propulsion or nuclear-electric hybrids. Some proposals suggest deploying interstellar catchers, thin, high-area collectors positioned beyond Earth's orbit to sweep up dust from passing interstellar comets. Even a few micrograms of such material could revolutionize our understanding of galactic chemistry. The biggest engineering challenge, of course, is speed. Interstellar comets typically enter the solar system at 25 to 35 kilometers per second relative to the Sun. Intercepting them requires tremendous delta V, a spacecraft capable of rapid acceleration, precise targeting, and autonomous navigation. Still, teams are already prototyping modular designs with pre-staged propulsion units that can be activated once a suitable target appears. The philosophy is simple: don't wait to build, wait to launch. Meanwhile, theoretical work continues to expand what we learned from 3I Atlas. By comparing its properties to Oumuamua and Borisov, scientists now understand there is a spectrum of interstellar bodies, from rocky asteroidal fragments to volatile rich comets. This diversity mirrors the range of materials found in young stellar systems, confirming that planetary formation everywhere produces similar debris. In this way, every interstellar visitor becomes a sample of a different planetary nursery. As these preparations advance, astronomers are also using Atlas data to refine the population models of interstellar objects. The revised estimate suggests our solar system is visited by at least one interstellar comet every few years, most too faint to see. That frequency makes the case for constant readiness even stronger. The next detection could happen tomorrow, next month, or 10 years from now. But it will happen. And when it does, we'll have a global network ready to act. Observatories will coordinate instantly. JWST or its successors will turn toward the new target within hours, and an interceptor probe, perhaps resting quietly at L2, will ignite its engines and race into deep space. For the first time in history, we may follow a traveler like 3I Atlas up close, watching its crust crack, its gases escape, its chemistry evolve as sunlight touches it again after millennia of darkness. The implications extend far beyond comet science. Each interstellar object carries not just material, but context, physical evidence of how other planetary systems evolve, what they're made of, and how matter circulates through the Milky Way. By studying them, we begin to understand the galaxy as a living system, where every star contributes to and draws from a shared reservoir of dust and ice. This transforms astronomy from an observational science into something almost ecological: the study of galactic circulation. In practical terms, it also means humanity's first contact with true interstellar material won't come from distant stars. It's already passing through our backyard. 3I Atlas proved that. The next object will let us touch it. What started as a faint moving dot on a telescope's detector has evolved into a global effort to connect the dots between worlds. The journey from 3I Atlas has taken us from chemistry to cosmology, from data to destiny. The next step is no longer about discovery, it's about engagement. In the following part, we'll explore what this engagement might look like in practice, how bringing interstellar material home could reshape our understanding of the origins of life, redefine planetary science, and even influence how we think about our place in a connected galaxy. For centuries, humanity has looked up at the stars and wondered what it might be like to reach them. But in truth, the stars have already been reaching us. Quietly, persistently, through interstellar messengers like 3I Atlas. And now, for the first time in history, we are preparing to bring a piece of another solar system home. The idea of capturing interstellar material isn't just an engineering dream. It's a scientific revolution waiting to happen. Imagine being able to hold, in a laboratory on Earth, a fragment that formed around another star billions of years ago. Every molecule, every isotope within it would tell a story written long before our planet existed. The concept builds directly upon the discoveries from 3I Atlas because of its unique carbon dioxide dominance and radiation-hardened shell. Scientists now know what to expect from such material. Highly processed ices, dense organics, and possibly preserved volatiles trapped beneath a protective crust. If a future mission can collect even a few grains of that matter, it would allow us to analyze its chemistry with tools far more precise than any telescope could ever achieve. NASA's Sample Return Roadmap already includes missions like OSIRIS-REx, which brought back dust from asteroid Bennu, and JAXA's Hayabusa 2, which sampled the asteroid Ryugu. Those missions proved that delicate collection and return from low-gravity bodies are feasible. The next frontier is speed, designing spacecraft that can intercept a fast-moving, interstellar object and still capture usable samples without destroying them on impact. Engineers have proposed several creative solutions. One is to use a cloud of aerogel panels, ultralight materials capable of slowing down and trapping high-speed particles intact. These panels could be deployed in front of a spacecraft as it flies through the dust coma of an interstellar comet. Even if the relative velocity is tens of kilometers per second, the aerogel's microscopic pores can cushion the grains, embedding them safely for return to Earth. NASA's Stardust mission proved this concept 2 decades ago when it captured dust from Comet Wild 2, and researchers are confident that new generations of aerogel can handle even higher speeds. Another approach involves mass spectrometry at the encounter itself. A probe could use onboard instruments to vaporize and analyze dust in real time, sending back detailed molecular fingerprints. That way, even if a sample can't be returned, scientists still gain direct chemical data, isotopes, organics, and mineral composition from the interstellar material itself. The possibilities are staggering. We could finally measure the ratios of carbon, oxygen, nitrogen, and hydrogen as they exist beyond our solar system. We could test whether the same chemical pathways that created organic molecules here operate under alien conditions. And we could directly compare isotopic signatures, cosmic fingerprints that might show whether all planetary systems share a common origin for their raw ingredients. For astrobiologists, this would be nothing short of revolutionary. The study of 3I Atlas revealed that radiation doesn't erase complexity, it fosters it. Long exposure to cosmic rays can transform simple molecules into complex organics, stable enough to survive interstellar travel, reactive enough to seed new worlds when warmed. If a return sample confirmed that such compounds remain intact, it would strengthen the case that prebiotic chemistry is a universal process, not an earthbound anomaly. Laboratories are already preparing for this possibility. At NASA's Goddard Space Flight Center, scientists have developed ultra-clean chambers capable of isolating microgram quantities of extraterrestrial dust. They plan to use infrared spectroscopy, chromatography, and mass analysis to study any captured material down to single molecules. Even one intact grain from a future interstellar comet could contain chemical clues older than the Sun itself. But beyond the scientific implications lies a deeper human one. Holding a sample from another star would change how we see ourselves. It would collapse the mental distance between here and out there. 3I Atlas reminded us that the cosmos is not separated into neat compartments of our system and theirs. It's a single, dynamic network where matter circulates endlessly, where atoms born in one star's death can become the seeds of another's birth. Bringing back a fragment from that shared circulation would be a tangible expression of unity between planetary systems. The global cooperation that would make such a mission possible is, in itself, symbolic. To intercept an interstellar object, agencies across continents would need to coordinate instantaneously, sharing data, computing trajectories, synchronizing launch windows. It would be a planetary effort to study a galactic phenomenon, an achievement of science on a scale that mirrors the subject itself. the benefits wouldn't stop at scientific curiosity. Understanding how interstellar materials survive could inform planetary defense strategies, teaching us how different materials behave under extreme heating or cosmic radiation. It could also influence future exploration technologies, including resource extraction from asteroids and comets. If we learn how to analyze and process radiation-hardened ices like those on 3I Atlas, we could one day harness similar materials for fuel or life support in deep space missions. All of this stems from a faint moving dot discovered by accident in a sky survey. That's the beauty of 3I Atlas's legacy. It turned a moment of curiosity into a blueprint for humanity's next great leap in exploration. The comet didn't just rewrite what we know about interstellar chemistry, it redefined what we can do about it. And while it has now vanished beyond our reach, its influence continues to ripple through every new proposal, every experiment, every telescope that scans the sky for the next messenger. Because somewhere out there, another interstellar object is already on its way. Unseen, untouched, carrying its own cargo of cosmic memory. When it arrives, we will be ready, not just to observe it, but to greet it, to follow it, to learn from it, and perhaps for the first time, to bring a piece of another star system home to ours. In the next part, we'll explore how discoveries like 3I Atlas are beginning to influence broader questions, not just about chemistry or astronomy, but about life itself, what it means, how it begins, and whether the ingredients scattered across the galaxy could make it inevitable rather than rare. For years, astrobiology has wrestled with a single haunting question. Is life rare or is it inevitable? The study of 3I Atlas has not answered that question outright, but it has shifted the odds by proving that organic chemistry can survive and even thrive across interstellar space. The comet provided real evidence that the seeds of life are not confined to one planet or even one star system. They may be woven into the fabric of the galaxy itself. When scientists first analyzed the James Webb data, they were struck by how resilient the chemistry was. Despite billions of years of radiation exposure, 3I Atlas still contained complex organics, molecules with carbon-hydrogen-oxygen bonds that form the backbone of biology. Under laboratory simulations, similar compounds dissolved in liquid water produce amino acids and sugars within hours. That means the fundamental steps toward biochemistry can begin not in oceans, but in ice, frozen darkness pierced by cosmic rays. If that can happen in deep space, then the galaxy may already be full of these prebiotic grains, each one a potential spark. In the quiet spaces between stars, the universe is constantly preparing ingredients for life, long before planets even form. 3I Atlas showed us that these molecules can endure the most extreme journeys, shattered, reassembled, and preserved until warmth returns. The implications ripple outward into every field. For planetary scientists, it strengthens the argument that early Earth's inventory of organic compounds didn't form solely here. Meteorites and comets, rich in carbon, likely delivered many of them. And if interstellar objects have been visiting for billions of years, Earth has been continuously sampling the galaxy's chemistry. Every fall of cometary dust, every impact of a small icy body could have contributed molecules from distant star systems. It's entirely possible that the first organic compounds on Earth were older than the solar system itself. For exoplanet researchers, the story is equally profound. If interstellar comets travel freely and frequently, they don't just visit us, they visit everywhere. Each young planetary system may be seeded with the same basic ingredients. That means the chemistry for life doesn't have to start from scratch on each world. It begins with a head start provided by billions of years of galactic exchange. The difference between a lifeless world and a living one may simply be whether conditions allowed those ancient compounds to flourish. This concept, once speculative, is now being folded into serious models of planetary evolution. Astrobiologists use data from 3I Atlas to refine simulations of prebiotic chemistry. They include cosmic ray processed ice as an input variable, material rich in CO2, methanol, and carbon chains. When exposed to ultraviolet light or liquid water, those molecules spontaneously form amino acids and nucleobases. The conclusion is hard to escape. The universe seems biased toward complexity. The Atlas also changed how scientists think about time. Before, the focus was on narrow windows, a few million years when planets are young and habitable. but interstellar chemistry operates on billion-year scales. The same carbon atom might pass through dozens of stars, comets, and nebulae before becoming part of a living cell. Seen this way, life isn't a local miracle. It's the natural result of a universe that never stops recycling. This view aligns beautifully with isotopic studies of meteorites, where pre-solar grains show that atoms inside our bodies were forged in long-dead stars. Now, with 3I Atlas, we can trace that lineage one step further, from nuclear fusion in stars through interstellar radiation chemistry to the assembly of prebiotic compounds. Life, it seems, is not just built from stardust. It's built from stardust that has traveled. Of course, there's a sobering side to this realization. If prebiotic chemistry is widespread, then so too are the conditions that could eventually give rise to life. Yet so far, we've found no direct evidence of living systems beyond Earth. This paradox only deepens the mystery. Perhaps the galaxy is full of potential, but actual biology still requires a delicate alignment of chance and stability. Perhaps the step from molecule to microbe remains the greatest leap of all. Still, 3I Atlas pushes optimism forward. If such molecules can survive the emptiness between stars, then life's precursors are resilient beyond expectation. And resilience, in the language of nature, is opportunity. It also reframes how we think about extinction. Even if worlds perish, if planets freeze, or civilizations fall, the matter that made them doesn't vanish. It disperses, reforming elsewhere, carrying traces of everything it once was. In that sense, the universe doesn't forget, it reuses, and every interstellar comet is a messenger of that continuity. Looking ahead, these insights are fueling new mission goals far beyond simple exploration. Future sample return efforts won't just search for organics. They'll look for patterns in isotopes and molecular ratios that can only result from biological or prebiotic processes. Detecting the same molecular structures across multiple interstellar visitors would strongly suggest a shared galactic chemistry and perhaps a shared destiny for life itself. The philosophical implications are vast. If 3I Atlas represents even one fragment of a galactic network of material exchange, then every planet, every moon, every living thing is part of a larger continuum. We are not isolated observers watching the universe from afar. We are the universe observing itself, built from its own traveling dust. That realization has begun to change the tone of astronomy itself. At conferences and in papers, scientists speak less about foreign systems and more about connected environments. The language is shifting from competition. Which system is more complex? Which planet more Earth-like? To collaboration, how each piece fits into the puzzle of a living galaxy. Atlas didn't reveal aliens, signals, or grand mysteries. It revealed something subtler, perhaps more important: context. It showed us that life, chemistry, and matter are part of a single unfolding process that spans light years and epochs. It grounded our imagination in data, yet lifted our understanding to cosmic scale. And in doing so, it reminded us that our search for life isn't about finding others. It's about recognizing that we already belong to something much greater. In the final part, we'll look forward beyond 3I Atlas to the dawn of a new observational era. We'll explore how upcoming telescopes, AI-guided networks, and interstellar probes will transform these lessons into action, ensuring that the next time a visitor crosses into our solar system, humanity will be ready not only to observe it, but to truly understand it. The story of 3I Atlas does not end with its fading light. In many ways, it was only the beginning, the opening chapter of a new era in astronomy, one defined by readiness, connection, and vision. Because from the moment this small, dark traveler slipped out of our sight, it left behind a challenge. What will we do when the next one comes? For the first time, humanity stands on the threshold of being able to answer that question. Not with speculation, but with preparation. Around the world, telescopes, satellites, and supercomputers are quietly building the architecture of a galactic observatory, network designed to detect and respond to the next interstellar object in real time. At the heart of that network will be the Vera C. Rubin Observatory, which will scan the entire southern sky every few nights. Its 3.2 gigapixel camera will detect faint objects as small as a few hundred meters across, far earlier than any survey before it. The data it produces, tens of terabytes each night, will be processed instantly by AI systems trained on the orbits of Oumuamua, Borisov, and 3I Atlas. When something moves in a way that defies solar gravity, the network will know within hours. But detection is only half the story. Equipped with lessons from 3I Atlas, space agencies are creating rapid response frameworks that can redirect telescopes and even spacecraft at a moment's notice. The European Comet Interceptor, resting at L2, will serve as humanity's first ready probe, able to spring into action the moment a new target is announced. NASA is developing its own Interstellar Object Observatory concept, proposing small, modular spacecraft that can launch within days on commercial rockets. Each would carry spectrometers tuned to CO2, organic compounds, and radiation-processed dust, the very chemistry that defined 3I Atlas. Meanwhile, a new generation of space-based infrared telescopes, like the planned NEO Surveyor, will extend our view beyond the visible spectrum, spotting interstellar visitors even before they glow. By the time they near the inner solar system, we'll already have weeks, maybe months, to prepare coordinated observations. This readiness marks a profound shift in how we think about exploration. For centuries, our species has waited for the universe to send surprises. Now, for the first time, we are building the ability to meet them halfway, to engage not by chance, but by design. The scientific benefits are staggering. With coordinated instruments observing across multiple wavelengths, the next interstellar object will be studied in complete detail. Its composition, rotation, outgassing, structure, and isotopic makeup mapped simultaneously. That data will let scientists test every theory born from 3I Atlas, from cosmic ray processing to organic survival, and perhaps even uncover new chemistry no one has yet imagined. At the same time, philosophical and cultural awareness is growing. As the public learned the story of 3I Atlas, the tiny visitor that carried billions of years of history, it captured imaginations around the world. Students, artists, and researchers began to see astronomy not as distant observation, but as participation in a living cosmos. In classrooms, teachers now use 3I Atlas as a case study in perseverance and patience. How something so small, traveling so far, could rewrite what humanity knows about itself. And that, perhaps, is the greatest legacy of all. For every number, every dataset, there is a mirror, a reflection of our own journey. We, too, are travelers made of cosmic dust, altered by time, carrying the chemistry of ancient stars within us. 3I Atlas reminded us that we are not spectators of the universe. We are its continuation. Technically, the comet is long gone now, a dim, tumbling ember receding into the black, heading toward the constellation Lyra. But its signal remains in our archives, its spectrum etched across petabytes of data that researchers still study frame by frame. Those numbers are silent, but what they say is enormous. That the galaxy is alive with motion, that even across impossible distances, knowledge can be shared, and that curiosity itself is a form of contact. As the next generation of telescopes prepares to awaken, scientists know what to expect and what not to. They know that the next visitor may not behave like Atlas or Borisov. It may be rockier or larger or strangely inert. It may reveal something that challenges everything we've learned again. That's the beauty of science. Every answer creates a new question, and every discovery becomes the foundation for the next. And so, when the next faint dot appears, when a new hyperbolic path cuts across the sky and alarms start to ping across observatories, the world will respond differently this time. Not with hesitation, but with readiness. Not with surprise, but with understanding. Because we've learned from the last one. In that moment, as telescopes turn and spacecraft ignite, we will remember the small interstellar traveler that changed everything. 3I Atlas showed us that the boundaries between worlds are illusions, that the same dust that forms distant comets also forms us. It connected science and wonder, numbers and meaning, observation and identity. And perhaps when the next one comes, and we finally meet it up close, when our instruments touch its surface, when we see its structure in full color, when we capture its chemistry with perfect clarity, humanity will take its first true step into the interstellar era. Because in truth, the era has already begun. It began the moment we noticed a faint moving light and realized it wasn't from here. and the moment we understood that Not From Here was never truly separate from home. That is the legacy of 3i Atlas, a single visitor that turned a planet of observers into a species of participants, and a reminder that discovery is not about distance, but about awareness. We don't need to leave the galaxy to find connection. It's already passing through us every day in silence, carrying stories written in light. And somewhere, far beyond the reach of our telescopes, that tiny wanderer continues its slow, unending voyage, still changing everything we thought we knew about the universe.